In this episode, we're going to connect an early boot concept that can feel abstract to two very real hardware situations where Linux behaves differently: embedded systems and graphics-heavy machines. When people first hear about the early boot environment, they often assume it is only relevant when a desktop fails to start. But the truth is that early boot design becomes most important when the hardware is unusual, the storage layout is non-standard, or the system has to bring up specialized drivers before it can reach a normal working state. Embedded devices and graphics-focused systems are perfect examples because they often have tight constraints, unique boot paths, and drivers that must be present at exactly the right moment. The exam likes this topic because it tests whether you can reason from the boot timeline, understand what early user space is doing, and recognize why different hardware contexts change what must be available early. By the end, you should be able to describe the purpose of initrd tools, explain why custom hardware changes the early boot problem, and interpret the kinds of failures you might see when that early environment is incomplete. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good way to ground this topic is to remember that the kernel begins booting with limited help, and it cannot magically access every driver and feature unless those pieces are either built into the kernel or provided very early as loadable components. The mechanism that often provides this early help is a temporary early user space image, commonly discussed as initial RAM disk, initrd, and initial RAM file system, init or amfs. And the key idea is that this environment is designed to get the system from the kernel's early startup into a state where the real root file system can be mounted. That environment typically includes scripts, minimal tools, and a curated set of modules that can load drivers, detect storage, and handle special requirements like assembling complex storage or unlocking protected volumes. What makes this exam relevant is that the early environment is not the full operating system, so it only contains what someone intentionally put there, and missing pieces can stop boot cold. The student-level insight is that early boot succeeds when the early image contains the right toolbox for the hardware and storage reality. Once you see it as a toolbox, you can reason about why different hardware contexts demand different tools. The phrase initramfs tools can sound like it refers to one specific utility, but it is better to treat it as a category of capabilities used to build, inspect, and maintain the early boot image so it matches the system's needs. Conceptually, these tools gather required kernel modules, include scripts that perform early detection, and bake in configuration that tells early user space how to find the real root file system. They also shape what the early boot environment does first, such as waiting for devices to appear, selecting the correct storage target, or handling special device discovery rules. This matters because boot is not just about having a kernel. It is about ensuring that the kernel can reach the operating system's files, and that often requires drivers for the storage controller and the file system type, plus any extra logic for a custom layout. Beginners sometimes assume that if a system can see a disk after it boots, it must also be able to see that disk during boot. But those are different moments with different available tools. Early user space exists precisely because the system may need help before the full set of drivers and services are available. Exam questions that describe a system dropping into an emergency environment often point back to this early toolbox being incomplete or mismatched. A key mental shift for custom hardware is accepting that early boot has a narrower margin for error than later runtime, because later runtime has more drivers available, more diagnostic ability, and more opportunities to recover. Early user space must succeed with limited resources and minimal assumptions, and it must succeed quickly enough to keep the boot chain moving. This is where hardware context becomes crucial, because embedded platforms and GPU-heavy systems can require specific drivers or initialization steps that a generic early image might not include. Even small differences, like a different storage controller, a different root device identifier, or a different requirement for firmware blobs, can change what early user space must do. When those differences are not accounted for, The symptoms can be confusing because the system may start booting and then fail at the handoff to the real root file system, making it look like the system is damaged when it is really missing early support. The exam is testing whether you understand that the early image is tailored, not universal, and that tailoring becomes more important as hardware becomes more specialized. If you keep that frame, you can read a scenario and ask which capability must exist early for this system to proceed. Embedded systems are a great example because they often use storage and boot paths that differ from the classic desktop or server mental model. Many embedded devices use flash-based storage, specialized boot firmware, or a compact root file system designed for reliability and size constraints. They may also rely on a device tree, which is a structured description of hardware provided to the kernel so it knows what devices exist and how they are wired on the board. For beginners, the important idea is that an embedded system may not have the same kind of automatic discovery that a standard PC platform provides. So early boot must be more explicit about what hardware is present and what drivers should be used. In that environment, initramfs tools are often used to ensure the early image contains the exact modules and scripts needed to bring up storage, mount the root file system, and handle platform-specific quirks. If the early image is missing a key driver, the device might not appear in time for boot, even though it could appear later if the system somehow reached a fuller runtime. That is why embedded boot problems often look like missing storage or missing root, even when the underlying flash is fine. The exam angle is that specialized platforms narrow the set of assumptions you can safely make. The constraints of embedded devices also shape what you expect the early boot environment to contain, because embedded systems frequently optimize for fast boot, minimal footprint, and predictable behavior. That means the early image might be intentionally small and contain only the pieces needed for that exact device, unlike a general-purpose distribution that tries to cover wide hardware diversity. This has a practical consequence. Changes that are easy on a desktop, like adding a driver or switching a storage configuration, can require rebuilding or updating the early image so boot still has everything it needs. Beginners sometimes misunderstand this and assume that installing a driver package in the normal file system automatically makes it available during early boot. But early boot uses its own packaged environment, and that environment must be updated intentionally. Embedded systems also often run with read-only root file systems or carefully controlled write areas, which means early boot scripts might handle mounting writable overlays or preparing temporary state areas. Those design choices are not merely performance tricks. They are reliability choices that help devices survive power loss and operate consistently. When a question hints at a device-like environment, small storage, or specialized boot, the safest reasoning is that early image content and early mount logic matter more than usual. GPU-focused systems introduce a different kind of early boot challenge, because graphics hardware can influence both the user experience and the boot sequence, especially when a system is expected to present a graphical login or a display output early. On the first mention only, that hardware is a graphics processing unit, GPU, and the critical idea is that a GPU is not just an output connector. It often requires driver support, firmware, and coordination with the display stack before it behaves as expected. In many Linux environments, the system can boot perfectly well without advanced graphics acceleration. But the moment you expect a graphical environment, the need for correct graphics drivers becomes more visible. This creates exam-friendly scenarios where the system boots but the display is blank, the resolution is wrong, or the graphical environment fails to start, even though the kernel and storage are healthy. In those cases, the question is often about layers and timing, not about a single magic fix, and the early boot environment can play a role if the graphics driver needs to be present early for a seamless transition. Even if the exam does not go deep into graphics driver specifics, it wants you to understand that specialized hardware support is often modular and timing sensitive. One reason graphics-related boot issues can be confusing is that there is a difference between basic display output and the full graphics stack that supports accelerated rendering and modern desktop behavior. A system might show basic output using a simple driver path, then later attempt to start a full graphical environment and fail when advanced driver support is needed. That can make it feel like boot itself is failing, when the truth is that the system reached user space but could not complete the transition to the intended graphical state. In exam terms, this is where your boot timeline matters, because you can separate a kernel and early user space failure from a later display system failure. However, early user space can still be relevant because some systems aim to enable early display features, handle special hardware initialization, or ensure the right modules are ready before the main user space environment takes over. If the early image contains the wrong module set or omits a required piece for the platform, the system might proceed but later run into a mismatch that shows up as a broken GUI. A beginner misunderstanding is assuming all graphics problems are application problems, when many are actually about kernel-level driver availability and the timing of when that driver becomes active. Keeping the layers straight prevents you from choosing answers that do not fit the stage described. Custom hardware contexts also highlight why initramfs images often include rules for device discovery and driver loading, rather than relying only on generic detection. The early environment may need to load specific modules in a particular order, wait for certain devices to appear, or prefer certain identifiers when choosing the root file system. This is especially relevant when storage devices are not instantly ready at boot, or when multiple devices exist and the system must choose the correct one consistently. In embedded environments, this might involve waiting for flash partitions to be ready or interpreting platform-specific storage layouts. In systems with complex hardware, it might involve ensuring that storage controllers and file systems are supported before attempting a mount. The exam often tests this indirectly by describing a boot that sometimes works and sometimes fails, which is a classic clue that timing or readiness assumptions are off. When you know the early image can include waiting logic, driver preloading, and discovery rules, you can see why rebuilding or adjusting that environment changes boot reliability. The student-level takeaway is that early boot is where Linux bridges the gap between generic kernel and specific hardware reality. Another major reason initramfs tools matter in custom hardware is that they help keep the system consistent across updates, because updates can change the kernel, the available modules, and the expected pairing between the kernel and the early image. If the early image was built for one kernel version and the system boots into another, the early environment may not have the correct modules or may reference drivers that no longer match. This is not about the kernel being bad. It is about alignment between components. The exam often frames alignment problems as a system that used to work and then stopped after an update or after a change, and the correct reasoning is that the boot chain depends on consistent sets of components. Embedded devices are especially sensitive because their images are often tightly packaged and tested as a unit, so a mismatch can break functionality quickly. Graphics-heavy systems can also feel sensitive because a driver update can change how the display behaves, and if the system expects a particular driver path to be available early, that expectation must be preserved. The mental habit to build is asking whether the early boot environment still matches the kernel and the hardware assumptions after a change. That habit helps you avoid blaming random causes when the scenario points to a predictable mismatch. Beginner misunderstandings often show up around the idea of where drivers and configuration live, because people assume that if a file exists somewhere on disk, the system can use it at any time, including during early boot. Early boot does not work like that, because the system may not have mounted the real root file system yet, and it may be running from a temporary environment in memory. That means anything needed before the real root mount must be present in that temporary environment, either built into the kernel or included in the early image. Another misunderstanding is thinking that embedded systems are simply small desktops, when in reality, they often use different bootloaders, different hardware description mechanisms, and different storage layouts that require specialized early logic. A third misunderstanding is assuming that GPU issues are purely about the desktop environment, when many display problems originate in kernel driver support and firmware availability. These misunderstandings matter because the exam uses them as traps, offering answers that target the wrong layer or the wrong time in the boot process. When you train yourself to ask what is available at that stage and what must be loaded before the next handoff, you naturally avoid those traps. You are learning to think like the boot process, not like a fully running system. A strong reasoning approach for these questions is to treat early boot as a sequence of requirements that must be satisfied in order and to connect each requirement to what could fail. The kernel must start, then it must access necessary drivers, then it must locate and mount the root file system, and then it must hand control to the normal user space environment. In embedded systems, the early requirements often include correct hardware description and correct storage driver support, while in GPU-heavy systems the early requirements might include a smooth transition to a graphical environment or ensuring a driver is available before a display manager starts. If a scenario describes a drop into an emergency environment complaining about missing root access, you can infer the failure happened before the real root mount, and the likely cause involves storage drivers, file system support, or device identification. If a scenario describes a system that boots but shows a blank screen at the point where a GUI should appear, you can infer that the root mount likely succeeded and the failure is later, but still possibly rooted in driver availability. This is how you use the boot story as a diagnostic framework without needing to touch tools. The exam rewards this because it is systematic and stage-aware. As you carry this mindset forward, it also helps you see why people talk about tailoring Linux images for different hardware contexts, because tailoring is not a luxury. It is how you guarantee the right pieces are available early. Embedded systems often ship as complete images where the kernel, early image, and root file system are designed together, and small deviations can break assumptions. Systems that rely on specialized hardware acceleration often require careful alignment between kernel version, driver availability, and the user interface stack, because a mismatch can produce a system that technically runs but does not deliver the expected experience. The phrase initrd tools, in this context, is really about the ability to create that alignment and maintain it over time. Even if you never build an image yourself, you can still answer exam questions by recognizing that early boot content is curated and that hardware specialization increases the need for correct curation. This helps you pick safer options, like choosing explanations that involve missing early drivers or mismatched components when the symptom points to early failures. It also helps you reject unrelated options that focus on user accounts or application settings when the system never even reached the point where those would matter. By the end of this episode, you should be able to explain why the early boot environment exists and why initramfs tooling matters more as hardware becomes less generic, whether that hardware is an embedded platform with unique storage and discovery requirements, or a system where a GPU plays a major role in the expected startup behavior. You should understand that the early image is a deliberate toolbox that must contain the right drivers and scripts to bridge from kernel startup to a mounted real root file system, and that mismatches in that toolbox can create failures that look like missing disks, missing root, or confusing partial boots. You should also be comfortable distinguishing between failures that occur before the system reaches normal user space and failures that occur later when higher-level services, including a graphical environment, attempt to start. Most importantly, you now have a repeatable reasoning method that fits the exam. Place the symptom on the boot timeline, identify what capability must exist at that moment, and consider whether the early environment would have had the right support for the hardware context described. If you keep that method steady, custom hardware questions stop feeling special because they become the same boot story with stricter requirements and clearer consequences.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.